All right, we are going back to our discussion of temperature. This is one of those areas that I can very quickly get on a rabbit trail. Again, helping you with your English. Rabbit trail, fancy term is called an excursus. We're not going to go on an excursus. We may go on a few rabbit trails. Same thing. Just for some people, they say rabbit trail and they go look for their 22. You're like, okay, that's not what we're talking about. We started yesterday with this idea of making a Celsius thermometer, or making a thermometer. And I said that if we took a thermometer, if we took a glass tube that had a volume of liquid in it that responded to temperature changes, that we could take that tube and put it in ice water, and then let it stabilize, and then take that tube and wherever the level of the fluid was in that tube, mark it and say, this is the freezing point. Because we started with this principle that if you have a container of fluid, actually I'll say just keep it with water. We have water, and it's got ice in it, and we have a tube that's in that water. That if the temperature if this is thoroughly mixed, and it has had time to go to a constant temperature, in other words, there's not a warm part here and a cold part somewhere else. It's all the same temperature. And it's got liquid and solid water in it. It's got ice and liquid water. That the temperature is 0 degrees Celsius or 32 degrees Fahrenheit. Always. It'll stay at 32 degrees Fahrenheit, 0 degrees Celsius until one of two things happens. Energy is added to it in the form of heat, and all of the ice melts. And once all of the water has converted from solid to liquid, if it's all liquid, and energy is still being added, once it's all liquid, then the temperature will begin to rise. We'll get into detail later, but all that energy that's added, while there is still ice, is used in transferring it in phase, changing it from liquid or from solid to liquid. So the temperature stays at 32. If we were to take energy out of it, we call that cooling. If we were to take energy out of it and this temperature were to get cooler, all of that energy that's lost would be, you would see that because this would begin to freeze up. But until the point where it is all solid, the temperature will remain at 32 degrees. Once it's all solid, it could cool below 32 degrees. Once it's all liquid, it could warm up above 32 degrees. But while it's a mixture of ice and water, it will be 32 degrees Fahrenheit or 0 degrees Celsius. So, like I told you yesterday, the image there is if you've got a cooler with ice water in it, and soda's in that, and you put your hand in there, you are experiencing 32 degrees Fahrenheit, 0 degrees Celsius. We know that's the temperature. In the same way, yesterday I listened to the video and I kind of messed up. I said, if you take food out of the oven and put it into boiling water, what I meant to say was out of the freezer, okay? Or out of the refrigerator. If you have one of these meals that's prepared, that you're to prepare, and it says to take that food packet, whatever it is, and put it in boiling water. What I'm showing there is, the bubbles coming up as it's being heated. We'll heat it over a single flame. Nice colonial candlestick, okay? So we're heating it with this flame. As it's heating, and it's starting to boil, as it's boiling, the temperature of that liquid is 100 degrees Celsius or 212 degrees Fahrenheit. That is the temperature until it's all boiled off. So whether it's boiling just a little bit or whether it's a rapid boil. Now, that is if it's totally mixed. What happens in real life, frankly, is the water that's closest to the flame heats up greater than, and so it's going to be cooler on the top and warmer on the bottom. But if you've got a mixing going on, and the boiling itself starts mixing the water. So the boiling process starts this convection of the fluid so that it all attains the same temperature. But once it's boiling, it is 100 degrees Celsius or 212 degrees Fahrenheit until everything boils off. So that's why you can put your glass tube with a fluid that reacts to temperature, put it in the ice water, and mark it. Let's say that the fluid comes up to this point. We could come in and mark our tube right there and say that is the freezing point. take the same tube, put it in the boiling water, and the level would rise, and we would end up then marking where that temperature is at, and we would end up with a tube with a fluid in it that has 2 marks on it, and at room temperature probably somewhere up in that region right there. We've got 2 marks on it. One mark representing, hey, when it's cool enough in here that the fluid falls to this point, water is freezing. This is the freezing point. And then when I heat it up to this point, the water is boiling. Now I've got a distance between those 2 points. And in the 2 different temperature scales, remember we said for, let's see, Fahrenheit and Celsius, the boiling point was 212. In Celsius, it's 100. Over here, the freezing point, this is boil and freeze. The freezing point in Fahrenheit is 32 degrees, and Celsius is 0 degrees. Maybe an easier way to see what I'm trying to do here, let me change the axes on this here. Let's change this to, this will be easier. Fahrenheit and Celsius, boil and freeze. If it freezes at 32 and boils at 212, here it boils at 100 and freezes at 0. How many units are between these 2 points in the Fahrenheit scale? Between 32 and 212. Right, so we take 2 from 2 is 0, 3 from 21 is 18, right? So there's 180 degrees of difference between this point and this point. So if I measure the distance between these two and separate it into 180 equal points, I now have a Fahrenheit thermometer because every point represents 1 degree. On the Celsius side, I go from 100 boiling, here's a 0 freezing, the difference is 100. So in the same way, if I were to take between these 2 points and divide it up into 100 equal segments, each segment would represent 1 degree of Celsius. Okay? And that's how we calibrate thermometers. We actually put them in freezing, in ice water, or put them in boiling water and read them and see, does it read 0 degrees when it freezes in Celsius and 32 in Fahrenheit? And when it boils, is it reading 212 or 100 respectively? So we can check the accuracy of it. Now, the assumption again was not only is the fluid thoroughly mixed so it's all the same temperature, but I mentioned yesterday one other caveat. Do you remember what that was? Pardon? Well, there was one other condition, one other caveat that was, for this to be true, the temperature has to be, the fluid has to be thoroughly mixed so it's all the same temperature, and I mentioned pressure. It has to be at 1 atmosphere of pressure. Using the analogy of the food again, I don't know how many people actually cook and bake anymore, but if you have ever noticed, on some recipes they have a set of instructions, a different set of instructions for high altitude cooking or high altitude baking. Usually it's in baking. And they'll say, you know, here's cook this or bake this for so many minutes at this temperature. And then below that they'll have high altitude instruction. And they'll give you a different temperature, or they'll give you a different time, or they'll give you different both. And the reason for that is they're actually compensating for the lack of pressure. It's a lower pressure as you go higher in the mountains. And so they vary the recipe to account for that lower pressure as you go up. Okay? Now, the thrust of what we're going to be doing here as well is converting between these two scales. And I mentioned this when we first talked about algebraic rearrangement of formula. I'm going to write down, first of all, the formula for Celsius, how to find Celsius if you're given Fahrenheit. Celsius is, this is equation 1.1 on page 32. Celsius is 5/9 Fahrenheit minus 32. Celsius is 5/9 the Fahrenheit minus 32. Now, I got to be honest, for some reason, I've got a mental block on this thing. It looks really simple, but I keep forgetting what it is. So every time I sit down and try to figure out how to convert between the scales, I've got to recreate this formula in my head. I've got to figure out the logic. I can remember the 5/9. There's another I'm not going to write it down here because we're going to derive it. But the other way to look at this is Fahrenheit is equal to 9/5 Celsius plus 32. We'll derive that in a moment. So in my mind, I'm going, is it 5/9 or 9/5? Is it plus or minus? Which one is it? And so I actually write it down and then have to think about it just for a moment to make sure I wrote it down correctly. In this case, what am I showing? Well, if I have a Fahrenheit, if I've got a temperature in Fahrenheit, and I multiply that by 5/9, is my result going to be greater than or less than the number in Fahrenheit? If I said, let me modify this just for a moment. Let me just pretend that it was just simply this. It's not, but let's pretend it's just simply Celsius is equal to 5/9 the Fahrenheit. And I said I've got a 150 degree Fahrenheit temperature. Is my Celsius temperature going to be greater than or less than my Fahrenheit temperature? Pardon? Yes, if I have a Fahrenheit temperature and I'm trying to convert it to Celsius, is my Celsius temperature going to be greater than or less than my Fahrenheit temperature? It's going to be less than, right? Because the fraction here is less than 1. I'm taking whatever I have in Fahrenheit and I'm multiplying it by less than 1 to come up with the Celsius. Look at over here. Here I have 180 degrees of difference. Here I have 100 degrees of difference. Guess what? I've got to multiply my Fahrenheit by something less than 1 in order to align it with only 100. I'm taking 180 and I'm aligning it with 100. Okay? So whether this is supposed to be 9/5 or 5/9, I very quickly see it has to be 5/9. Why? Let's say I had 212 degrees Fahrenheit. Well, guess what 5/9 Fahrenheit is? It's going to be close to 100. Not exactly, close to, because we remember we modified this formula. So I know that the 5/9 portion is right. Now here's the other part of it, which I just erased. Degrees Fahrenheit minus 32 degrees, right? Degrees Fahrenheit minus 32. Remember, this is a quantity. 5/9 times the quantity Fahrenheit minus 32. And the way I remember that it's quantity minus 32 is this. When water freezes, what is the temperature in Celsius? 0. So this has to be 0. If I multiply 5/9 times something, it has to equal to 0, right? So what does water freeze at in Fahrenheit? 32. So Fahrenheit minus 32 has to equal 0. So it has to be 32. See? So that just, for me, that's how I go through every time I write it down to check it real quick. Hey, I take my Fahrenheit and multiply it by less than 1. I got this one right. It's not 9/5, it's 5/9. Hey, when this is 32, this has to be equal to 0. Is 32 minus 32 equal to 0? Yes. Okay. Now my formula is right. Or you can just memorize it now before you have the mental block that this old 52-year-old guy has and said, no, Celsius is 5/9 Fahrenheit minus 32. 5/9 quantity Fahrenheit minus 32. That's important because when we rearrange this to solve for Fahrenheit given Celsius, the quantity mark is not in there, right? Now, so the 5/9 accounts for the differences in each degree going from between 180 to 100 or vice versa. And this aligns us with our 0 mark right here. So if I were given a Fahrenheit temperature, let's go ahead and work the boiling point. What is the boiling point in Celsius if it is 212 degrees Fahrenheit? Well, if all we do is plug in our known 5/9 quantity 212 degrees minus 32 degrees, right? If you didn't know that water boils at 100 degrees Celsius, but you did know it boiled at 212 degrees Fahrenheit, this is how I'd figure out what the Fahrenheit is. Equals 5/9. 212 minus 32. We've already said that's 180, right? So, so algebraically, there's many different ways you can solve that quickly, but you can go down here and say, well, 9 goes into 9 once, 9 goes into 180 20 times, and that equals 100. So when the temperature is 212 degrees Fahrenheit, the temperature in Celsius is 100 degrees Celsius.
Can you do that again, please?
Which part? So I have the formula, Celsius equals 5/9 quantity Fahrenheit minus 32. And the problem would say something like this. If the water was boiling at 212 degrees Fahrenheit, what is its temperature in Celsius? So you're given the Fahrenheit, you need to solve for Celsius. So whatever the temperature you're given, you plug that in. I said the temperature is 212, so I plug that in for whatever the Fahrenheit temperature is. I put that in the equation, and then I solve it. So it's 5/9 times the quantity, 212 minus 32. Well, 212 minus 32 is 180. So it's 5/9 times 180. I could solve this by going, you could say 5 times 180 divided by 9. That's one way to solve this, right? Let me get rid of this just so you can. So it's 5 times 180 divided by 9. You could also see it as 5 times 180 divided by 9. And if I do that, I can say, well, wait a minute. 9 goes into 9 one time. 9 goes into 180 20 times. And 5 times 20 is 100 over 1, or 100. So does it check? When the temperature is 212 degrees Fahrenheit, the temperature in Celsius is 100 degrees Celsius. Yes, it checks. So given Fahrenheit, solve for Celsius, you're going to use this formula and plug in whatever Fahrenheit you're given, solving for Celsius. Now the other side of that is, we not only convert from Fahrenheit to Celsius, but we occasionally convert from Celsius to Fahrenheit. You can memorize the other formula, or it's a good process, is to convert this formula to solve for F, solve for Fahrenheit. Okay? Now how would we do that? We've already done this once, so I'm going to walk through it a little quickly. We can go ahead and multiply both sides of the equation by 9/5 to get rid of this coefficient over here on this side. If I multiply both sides by 9/5, if I multiply both sides by the same thing, I haven't changed anything, right? It's 9/5 times this whole over here. But because it's bracketed out, 9/5, let me rewrite it a little simpler. 9/5 Celsius equals Fahrenheit minus 32. That's what it reduces down to. Because the 9/5 times the 5/9 cross multiplication, it's 45 divided by 45, it's 1. That's the nice thing about doing cross multiplication, is you take the coefficient, you invert it, and multiply both sides by it. It disappears. Boom. So what we're left with is this right here, the quantity F minus 32. I want to get Fahrenheit all by itself, because that's what I'm trying to solve for. You always put the variable you're solving for all by itself on one side of the equal sign and get everything else on the other side. So in this case, I'm trying to get Fahrenheit, F, all by itself and get everything else on the other side. And I can do that by adding 32 to both sides. And so we've got 9/5 Celsius plus 32 equals Fahrenheit. Or the way you should be able to rearrange that, Fahrenheit equals 9/5 Celsius plus 32. So given this, given a Celsius, I can now solve for Fahrenheit. Well, let's go ahead and try boiling point again. If the boiling point of a fluid, in this case water, is 100 degrees Celsius, what is the boiling point in Fahrenheit? Well, if the boiling point is 100 degrees Celsius, and I plug in the 100 for the Celsius, plus 32. 5 goes into 5 once, and into 100 goes in 20 times. So it's equal to 180 plus 32, which is 212. Okay? So when I rearrange the formula, I'll go ahead and plug in one of these known points. plug it in and see if I get the right answer. And if I do, then the formula I've written down is correct. Because it's not always going to be the nice, simple 212, 32, or 100 and 0. It's going to be something in the middle, higher, lower. You don't know where it's going to go. To just be able to use the formula, either the Celsius equals 5/9 quantity Fahrenheit minus 32, or Fahrenheit equals 9/5 Celsius plus 32. Those are both in your book, page 32 and 33. And also, remember, at the end of every module, there's a page of key equations and tables. For Module 1, it's page 37. After the last piece of text, it gives you these two key equations, or it gives you this key equation, and you can use it then to rearrange it for the other. So equation 1:1, Celsius equals 5/9 quantity Fahrenheit minus 32. However, we seldom actually work in Fahrenheit or Celsius, but you need to know how to get between them. What we tend to work in is called Kelvin, the Kelvin scale. Now, Kelvin is a little bit different, and it's, I'm going to say it's going to be essential, it's vital. But so F is Fahrenheit, C is Celsius, K is Kelvin. Kelvin is based upon the Celsius scale. Okay? What I'll tell you is between the boiling point and the freezing point in the Kelvin scale is 100 units, just like it is in Celsius. So 1 degree of change in Kelvin is the same as 1 degree of change in Celsius. So why do we have two scales? If 1 degree in Kelvin is the same as 1 degree in Celsius, why the difference? Well, Kelvin is what's known as an absolute temperature scale. You may have heard the phrase absolute zero before. Where is absolute zero? Absolute zero is at 0 degrees Kelvin. 0 degrees Kelvin. So the formula for moving back and forth between Kelvin and Celsius is that Kelvin is equal to degrees Celsius plus 200, and I want to get it to the right point, 273.15. Excuse me. Kelvin is Celsius plus 273.15. Now let's think about that for a minute. Over here we've got the freezing point and the boiling point in Fahrenheit and Celsius. I'm just going to erase this and slide it over a bit so we have a little bit more room. So in Fahrenheit, Celsius, and I'm going to add to this Kelvin. In the Kelvin scale, it's the Celsius plus 273.15. So at what temperature Kelvin does water freeze? I take this formula. If my Celsius is 0, because water freezes at 0 Celsius, I put 0 plus 273.15. The temperature of freezing of water is 273.15 Kelvin. And boiling point is 100 degrees Celsius, so it is 373.15 Kelvin. Here's the deal. Do you ever experience temperatures lower than the freezing point? We have. I mean, we moved here from Buffalo, and we used to live half our year below 0, but here, you guys get a month or two where it's below 0, a temperature below the freezing point. Okay? And what ends up happening is, in Fahrenheit, you eventually get to a below 0 point, but we even experience below 0 Fahrenheit. But anytime you're below 0 in Celsius, anytime it's below freezing point of water, it's a negative number. So you can get negative numbers in Fahrenheit, and you can get negative numbers in Celsius. But you can never get a negative number in Kelvin. You can never get a negative number in Kelvin because there's no such thing as something that's, for now we'll use the phrase colder. It's not really colder, but for now. There's nothing colder than 0 degrees Kelvin because we can't even get to 0 degrees Kelvin. Okay, this is where philosophy starts to enter into chemistry for a few moments, so bear with me. What I want you to think about is that these two scales are based upon, well, first of all, Fahrenheit. Why 32 degrees at freezing? Why, where'd that come from? Why isn't this 0? For me, that's where I think, why isn't this 0? So let's not consider Fahrenheit, because we all know Fahrenheit's the English system's kind of like, I think Celsius or the metric system is a much more thought out system, because it starts at least 0. And for me, the idea that water freezes at a temperature that's 0 makes sense. It's a benchmark for something. Okay. Kelvin, what I want you to think about is the Kelvin, down at Kelvin, at 0 degrees Kelvin, is not where water freezes. It's where everything freezes. Everything. In Celsius, you've got water, the water's moving around, and at 0, it turns solid. And we'll talk about what it means to be solid, liquid, and gas in a couple modules. But for right now, it just freezes solid and doesn't move in the same way we're used to. At 0 degrees Kelvin, everything stops moving. Everything. Electrons stop moving. Electrons stop spinning. Time stops at 0 degrees Kelvin. There's no such thing as time anymore. Because we said in the beginning of class, what's up, what's down, depends upon your perspective, right? Time only has meaning if there's motion. If nothing is moving, if nothing is happening, what is time? Scripture says, in the beginning, God. And some philosophers go, God existed before there was anything. God exists outside of time. Why? Because there was nothing and yet there was God. He existed, but there was no such thing as time until there was something. And that's why there is a beginning. Not the beginning of God, but the beginning of matter and time. There is a movement from the nothing to the something. And somehow God is outside of the nothing of matter and material. So conceptually, we've got something, and as we get it colder and colder and colder, that's a way to think of it. We're taking energy out of it, energy out of it, energy out of it, to the point where stuff stops moving, atoms and molecules stop vibrating, they go solid. Electrons are no longer spinning around the nucleus, they go solid. The electrons themselves are no longer spinning. As they spin around the nucleus, it goes solid. There's no energy left. Time stops at 0 degrees Kelvin. It's the absolute 0. And we don't even know if it really exists. We're going to talk later about scientific method and extrapolation. But there's the idea of an absolute 0 is a theory that we don't know to be true because we've never been there. We've never been able to get to absolute 0. The best we can speculate are things like deep space, which I believe, don't hold me to this, but I believe deep space is considered to be about 3 degrees Kelvin. Deep space, 3 degrees Kelvin. There's energy there. It's weak, there's not much, but there is energy there. 0 degrees Kelvin represents a place where there's no energy in the stuff. And stuff as we know it stops to become stuff like we know it. Now when we actually talk about this later, we'll get into a little bit more of, again, extrapolation, how this fits. But just right now, realize that we've never been there, but all the different tests that we've done on different materials, different matter, we talk about, for example, the volume. We use the balloon with volume, right? As you take a volume of gas and as you cool it, it takes up less volume. And it makes sense. You heat it up, it expands. You cool it down, it gets smaller, gets smaller, gets smaller, gets smaller, gets smaller, gets smaller. And as we make a chart and plot all this stuff out, we'll talk about later about, let's say that this is a graph that represents the volume and the temperature. And as we cool a volume of gas, let's say it starts with a certain temperature and volume here, but as we cool it, it moves in this direction, getting smaller and smaller and smaller and smaller and smaller and smaller. And we don't have the ability to get it any colder than that, right? I mean, there's only so many air conditioning units and refrigerator freezers and things like that we can do. We just can't get that cold. Again, think of it as cold for now. We just can't get that cold. But if I told you that the volume followed this kind of a line and we only got to there, and I said, speculate for me. Make a logical guess. What do you think is going to happen after that point? Well, you'd probably say, I think it's just going to keep on going down like that. And I say, that's great. But when you get to 0 temperature, how much volume do you have? 0 volume. What is chemistry? The study of everything that has volume and mass. We've just moved into the domain where stuff that was chemistry is no longer chemistry. Because what had volume no longer has volume. How do we understand something that doesn't have any volume? It's philosophical. We've never been there. We don't know. The fact that we think that happens, we've never been there, so we can't say that is what happens. We just think that's what happens. I mean, for all we know, we get to a certain point here, and guess what? Boom, boom, the volume gets huge again. But we've never been there. But the best we can tell, this is the trend. And if this is the trend, there's actually a place where stuff no longer takes up volume. Where stuff that's made up of matter that's in motion all the time, even if it's frozen, it's in motion all the time, no longer is in motion. Time, which has meaning in motion, doesn't have any meaning when there's no motion. Okay, so that's good enough now for philosophy and chemistry. We'll maybe for fun we'll pick up on that as another excursus, another rabbit trail in the future. Let's go ahead and work a few problems using conversions and between Celsius, Fahrenheit, and Kelvin. The only thing we have left, let me just do this part and we'll work problems till the bell, is about the nature of scientific law. And what the biggest thing I want you to pull away from this is page 34, 35, and 36, is that basically what this comes down to is that scientists develop laws, it says, through experimentation and observation. First of all, they make a hypothesis. Remember we did that first day, I blew up that balloon, I said, does it have mass or not? You might have said, yes, it does, or no, it doesn't. I put it on the triple beam balance, and boom, guess what? It had mass. So you had an hypothesis. It either will or will not have mass. Then we put it on the beam. You said, guess what? My hypothesis was true, was shown to be true or was shown to not be true, right? And then we said, okay, well, if I got it wrong, I would change my hypothesis and I'd do another test to check it. Do another test to check it. And then after a while, after you have the hypothesis, you have that hypothesis as your educated guess. You go on and do it some more and do it some more and do it some more. Your hypothesis becomes a theory. Then you take your theory and you test it more and test it more and test it more and test it more. And over time, the theory becomes a law. Okay? What this basically means is we just have levels of assurance that what we believe to be true is true. That if I drop a BB and a bowling ball, both from the same height, which is going to hit the ground first? The answer is they're going to hit at the same time. The mass does not affect how quickly it accelerates and hits the ground. More the shape than the mass. So I have two objects, drop them, boom. Wait a minute, I expected the heavy one to hit first. I was wrong. Try it again, boom. Hey, they hit at the same time again. My hypothesis was really wrong. I believe that they're going to hit the ground at the same time. Boom. They did it again. Boom. They did it again. Boom. They did it again. Guess what? I have a theory that how quickly they hit the ground isn't based upon their mass. It's based upon something else. Boom. Did it again. Boom. Did it again. Do it so many times that my theory then becomes a law. People say, oh, everybody knows that when you drop them when you drop them, they're going to hit the ground at the same time. But that's just accepted. We don't even question that anymore. It becomes a scientific law where people start using it and saying, well, of course I know because Ray's proven on his studies that they're going to hit the ground at the same time. Therefore, we know that when we launch this missile, we start applying it, saying, well, he's proven, we've shown this law. Other people other than Ray, the rest of you have joined him in his research, and you're all getting the same answer. And because it happens to be true all the time, we say it's a law, and so nobody questions it anymore. And you may have heard the difference between theories and laws, right? For example, when we talk about gravity, we talk about the law of gravity. When we start talking about gravity, we tend not to stop and go, is gravity real or not? Let's talk about whether or not there's gravity. I wonder, if I drop this marker, if it'll hit the ground, or will it just float in place? We don't do that anymore. We've all come to accept and use the law of gravity. We expect things to fall, and we assume it's true all the time. Now, that doesn't mean that sometime in the future, we're not going to learn that our understanding of what gravity is wrong. The way we understood it just happened to match what we saw, but it could be fundamentally wrong. But we use it. So as you go through the elevation from a hypothesis to a theory to a law, it's really based upon experimentation and use. Your experimentation, your peers' experimentation, other people's experimentation to prove something over and over and over again so it becomes a law. Now they use in here the example of maggots and meat. If you remember that from the reading. They use maggots and meat, and they said, you know what? There used to be the theory of spontaneous generation, because people would look and they would see rotting meat and they would observe the maggots on the meat. And it appeared like the maggots were just coming out of the meat. And so the theory was maggots come from old meat. Old meat spontaneously generates maggots. Maggots come out of the nothing and become something, and the something comes from the meat. So it's like meat incarnate, right? The meat comes to life in the form of maggots, which then eats the meat. But there was a time when that was the prevailing theory, because every time people looked at meat that rotted, maggots started coming out of it. So maggots must come from the meat. And they took the meat and they hung it. Because some people said, well, the maggots must crawl to it and get on it somehow and come from outside of it. They said, no, that can't be the case either, because we hang the meat, so nothing can crawl to it, because maggots crawl, right? The maggots couldn't have crawled on the meat because we've hung it from a tree by a rope, and maggots couldn't just come across the ground to it. The rotting meat still has maggots on it. That proves that maggots come from rotting meat. It was actually the work of Louis Pasteur, who as a Christian said, you know what, God created something out of nothing, but God's creative plan is already in place, and nothing comes from nothing. These have to be coming from something. Something. And he questioned whether or not the maggot, whatever became maggots, was in the meat or not. By isolating it, what they eventually figured out was, you know what? Flies that land on the meat deposit the eggs, and those become maggots, and maggots are future flies. They fly to the meat. They don't have to crawl to the meat, right? That's why we've got milk and it's pasteurized. Pasteurized milk, the process that Louis Pasteur came up with, is they take the milk and they basically cook it and kill the bugs in the milk so that by the time you get it, it lasts longer, because the bugs that would become nasties have already been killed. So rather than drinking live parasites, you drink them dead so they don't hurt you. Now, you may not want to think about every time you drink milk, you're drinking stuff that's been killed so that it doesn't kill you, but it lasts longer. The stuff that makes it go bad, the stuff that makes it sour, that is actually organic. Those are organisms. That's alive. And Pasteur said, you know, if we kill it before it grows, it'll last longer. It'll get infected by other things and spoil, but it won't spoil from what it starts with. It'll spoil from what comes to it. So through the process of pasteurization. The last section here in the book talks about this experimentation in the scientific method, that we have a purpose, we have a goal of something we're trying to solve or answer, and so we form a prediction, a hypothesis, and then we do our experiments. We look at our experiments and say, does this prove or disprove our hypothesis, and we come to a conclusion. And the scientific method does it over and over and over and over again. And that's why also I said between hypothesis, theory, and law, that is why we have things like the theory of evolution, not the law of evolution. Okay? Because in here, the scientific method means you need to be able to observe it and to replicate it. For something to be a law, you have to be able to observe it and replicate it. So the idea of observing evolution and replicating what has happened falls outside of our ability. It's a theory. We have a lot of things that are theories, but they have not come to the level of repeatability for observation for it to become a law. So you may hear people talk about the theory of this and the theory of that, or the law of this and the law of that. It's because it's been able to attain the status of a law because it's followed the scientific method. A lot of drooping today. Excuse me just a second. Ike, arms actually have to be out through the sleeves. I know you've been doing it for a couple days, but I haven't called you on it, but thank you, sir. Same thing, too, with jackets, ladies. I mean, it'll tend to happen in here as it gets colder. You know, you're working between being too warm and too cold. Wearing the fleeces, sometimes people like to reverse them and put their arms through them backwards so that they're covered in the front and open in the back. Some people just leave them in their lap and stick their arms through them. Sorry. But that's still dress code issues. Let's work a couple of the on your owns then that deal with temperature so we can do some conversions. The normal body temperature, on your own 115. Normal body temperature is 98.6 degrees Fahrenheit. What is that in Celsius? We had Celsius is equal to 5/9 quantity Fahrenheit minus 32, right? So in this case, we can look down to our formula, and in every instance where we see a Fahrenheit, we can replace it with what we've been given. The known here, the given here, is 98.6 degrees Fahrenheit. So we're going to take the formula and plug in that 98.6 degrees every time we see Fahrenheit. It's 5/9 quantity, 98.6 minus 32. So let's just go ahead and continue to do the math. I'm going to go ahead and leave the coefficient out front. It's going to be 5/9 quantity, 98.6 minus 32. It's going to be 0.6 something, 66, ooh, 65.6. So 6, no, 32 to 6, yep, 66.6. Right? So 5/9, 66.6. So it's going to be greater than or less than 66.6. It's going to be less than. It's going to be a little more than half of 66.6. Anybody have a brain? Electronic brain? I'm going to flip back to the answer key. Just use that. So we are at 115, 37.0 degrees. So 98.6 degrees Fahrenheit is the same as 37.0 degrees Celsius. By plugging in the Fahrenheit in the formula, solving. Now, why did I not use 37 degrees? Not as precise. Very good, Ray. It's not as precise. I was given 98.6. My precision, okay, was to the tenths place. Here I'm multiplying by a constant, so the precision doesn't come into play. So it's going to be 5/9 times, well, right here, again, 32, it's by definition 32, so we're not going to include that consideration. The only number we have to consider is the precision of our original, and the precision of our original is to the tenths place, and so I have to take my answer out to the tenths place. So 37 degrees would be true, but 37.0 degrees is both true and correct. 116 says that rubbing alcohol boils at 180.5 degrees Celsius. What is the boiling temperature of rubbing alcohol in Fahrenheit? So this equals how many degrees Fahrenheit? I've got to derive the Fahrenheit formula, right? Fahrenheit is 9/5. Celsius plus 32. I know that because if Celsius was 0, I would have to have 32 degrees Fahrenheit, so that has to be plus 32. So there's my formula for converting from Celsius to Fahrenheit. Let's just plug in 180.5, so it's 9/5 times 180.5 plus 32. $356.9. Let's stop just for a minute and see, does that make sense? Well, 9/5, that's almost 2 times, right? A little bit less than 2 times. 2 times this would be 360. So 360 plus 32 is 392, but it's going to be a little less than 392. It's reasonable. That's a reasonable answer. So I look for reasonability, and I also then punch in the numbers and find out what it gives me exactly.